Hey guys, so here's this quick video, as you probably already know, is going to be on transformations, and what I want to do real quick is just kind of show you what these transformation rules are. There's a few of them. You have some reflection rules, and you have some horizontal vertical shifts that we're going to be doing. So as we get going here, one thing that you hopefully have already know, you understand how to graph lines. So I have three little things here that are called parent graphs. The first one is y equals x. That's a linear equation, and what we're going to be doing with this function and those other two is we're going to be applying transformations to them, which means we're going to move them around, stretch them, compress them, flip them, all sorts of stuff. Now what's really cool about this is that you have a specific method for graphing lines that you've learned over the years of slope-intercept form, standard form, and different ways you can approach those types of graphs. You've also learned how to graph quadratic functions. You may have learned to factor to find the zeros. You learn how to find the vertex, especially if it's in standard form, ax squared plus bx plus c, and you're able to plot those points. With transformations, what we're going to be able to do is graph all functions. It doesn't matter what function we're dealing with, as long as we know the base function, which is called the parent function, which are those three functions that you'll see on the screen right now. As long as you know those functions and you know the translation or transformation rules, you can graph any function you want. So what we're going to do to get started is talk about those parent graphs, and then we'll talk about the types of transformations that you can apply to those. So the first graph, as you see here, is a line graph. It is the most basic form of a line, y equals x. And just to kind of delve into this a little bit, this is a slope of 1. I don't need to write a 1, it's 1. And then it has a y-intercept of 0. If I put this into y equals mx plus b form, again, m is 1, and your y-intercept is going to be 0. And you can see that in my graph. Okay, the second graph that you've seen before, hopefully, is going to be a quadratic function. And it's not even like 2x squared plus 3x minus 5 or something like that with all sorts of different stuff going on here. This is just the most basic form of a quadratic function, which is a parabola with a vertex right here at 0, 0. I'll even put that point in there. Okay, now there's a third one. Maybe you've seen it, maybe you haven't. I mean, we've done some solving equations. Maybe I've already talked about it in class, or your teacher has. But this is an absolute value graph, and it kind of looks like, and it has a lot of the same properties as a quadratic function, which is kind of why we're doing these together with quadratics, because these are, as you can see, very similar. The only difference is that a absolute value is made up of two rays instead of a smooth curve. So basically what you do to graph this is you take the equation y equals x, which would be like this, and you take that, the negative values, because absolute value will make it positive, it represents distance from 0, you make it positive, which moves it up here. So it's taking that line equation, that parent graph for a line, and it's just flipping that negative values on that line. I'm going to go erase that though, because, well, that's not what this graph is. So that's your parent graph, and the next thing we're going to do, and I have the rules written down here for your notes, but I'm going to go back here and show you some of this stuff. And talk about translation rules. So first off, just we can use absolute value as an example. I have this page first about the absolute value and the translations that you can do to it. Again, these are all the translation rules, kind of, not all of them, but these are some of them kind of plugged in here. You'll see some graphs, but actually probably what I should do first is talk about transformations in general. What that means is I'm not talking about transformations just in terms of lines, parabolas, and absolute values. I'm talking about in terms of functions, because as I said before, this concept that we're going over right now is you're going to be able to use it on any function. So we're just getting started with this. So the first type of translation that you're going to see is a vertical translation. And normally it's denoted with a k value, so that's what I have here. I have a k value to represent it. So if you have a vertical translation, you want to know this, you're going to have that f of x plus k. That f of x is whatever the graph that you're graphing is. So it could be x squared plus k, absolute value of x plus k, ones that we haven't done yet like x cubed plus k, the square root of x plus k. It's just that function with a number added or subtracted from it. So notice if you have a positive k, that means you're going up, and a negative k means you're going down. One easy way to remember this is think of your f of x as your y value. You do the function, you get an output, but then you're taking that output and you're adding or subtracting something to it. So that's going to be your vertical translation. Again, that's denoted with a k. You can kind of see what it looks like right here. If you just have your basic, this green graph is your parent graph. If you're going up k, you just slide it up. You go down k, you slide it down. That's as simple as that. Okay? Next up is your horizontal translation. Sometimes people mess these up. I want to make a note before I even really go over all this. This note down at the bottom, please pay attention to that, because horizontal shifts are opposite of what you might think they are. But first off, here's what they look like. You're going to be adding or subtracting a number inside the function. A quick example of that would be something like this. Instead of x squared, you might have x minus 2 squared. Y equals, obviously. And notice that number's in the function. It's being squared. So it's in the function. It's going to be squared because it's inside that square in the base. So anyway, with this one, what you have to understand, if I'm subtracting 2 from x, what you actually have to do to the x is you need to kind of counteract that minus 2 by making your values 2 bigger to get back to where you originally were. What that basically means is that if you have a positive h, which I have down here, I'm just highlighting things so you can kind of tell where I'm at on the screen. So you don't always have to highlight these things if you don't want to. But if you have a positive h, that just means you're going left. That's always opposite. It's counterintuitive. If you're going negative h, so I'm going x minus 2, like the example I have up above in the red, that would be going right 2. So minus h means right h. And you can see on these graphs here, I'm just taking this graph and I'm sliding it either to the right if you do x minus h, or you slide it to the left if you have x plus h. So understand how those horizontal shifts work. It's always opposite. Whereas the k value, the vertical shift, is not opposite. And again, because these don't change no matter what function you use, get used to it, because it's never going to be different no matter what function we're working with. Next up, we have our vertical stretch and a vertical compression. And I want you to think of this as if you take the graph and you pull on it vertically, that's a vertical compression or vertical stretch. You're stretching it from the top and the bottom. A vertical compression is like if you take your function and you start to smash it. It's going to flatten it out. So a vertical stretch, so you know the rule on this, is when you have a number being multiplied by your function. If that number is greater than 1, everything's going to go up faster or go down faster. So it's like you're stretching it vertically. If that number is in between 0 and 1, it's like you're compressing it vertically. It's going to make it go up or down slower. So it's going to get wider. So again, if you're looking at some graphs here, you'll see a vertical stretch. The bigger the number, the more it's stretched. So again, think of these values here on my orange part of the graph. Take it like you're taking your graph at the bottom and the top of these little miniature vertices, and you're pulling on them. Well, it's going to stretch it in both directions. The bigger the number, the more force you can think is being added to that stretch. So that's going to be a vertical stretch, and a compression, as you can see, it'll make it a little bit flatter. So you see that green graph, that's your original function. Well, if you multiply by a fraction, it's like you're smashing that graph, so it's going to get a little bit wider, and the values are going to go down. They're not going to go up as far or as fast. So that's going to be your vertical compression, and again, that just is a number being multiplied that's by your function that's somewhere between 0 and 1. Some people may ask, what happens if it's negative? Well, if a is negative, as you can see down here, that is going to be a reflection. So that means you've reflected it over the, in this case, the x-axis. So, you got your compression, you got your stretch and all that, but if it's negative, again, it's a reflection. So if I was taking this green graph, I'll do a lighter green, it would look something like this. I know it's not perfect because I don't have enough room down there. You see, like, it's taking that graph and it's flipping it over the x-axis. So that's, you know, some questions that you get with that piece as well. Okay, so again, a little bit more as you're going on in here. You can take something now and say we're going to take a number. We're going to multiply it by the input. Now this is one we're not really getting into too much. So think of this as just like a FYI situation, just so you know. We do this a lot more with trig too. But if you're multiplying something by the x value, if that number is in between 0 and 1, then you're going to have what's called a horizontal stretch. So those things happen as well. Okay, so again, notice here it's always counterintuitive again. And if you have a horizontal compression, that's when your number that's being multiplied by x is greater than 1. So think anytime it's in the function, it's always kind of opposite of what you would normally think. But like I said, this we don't deal with as much, so don't worry about that, which is why I'm just kind of skimming past it. Now, I did want to bring up again those reflections, because that's the one thing I mentioned, so this will be tested. So the reflections now. This is when that a is negative. You see a is negative, it's like you have a negative number in front of your function. That's when you're going to have an x-axis reflection, which means your graph is getting flipped over the x-axis. If you have a y-axis reflection, well, that's because the negative is inside the function. And again, easy way to remember this. Think of this as negative y. You're taking, and I want to even call it negative, so I call it opposite y. Your y values are going to get switched. Well, if you think about your xy plane, if you switch to the y value, you've actually gone over the x-axis. Here, think of this, well, it is what it is, it's opposite x. So you're flipping over the y-axis, because when you take a value, an xy value, and you switch the x value, you actually are switching over the y-axis. So anyways, you're looking at this graph, you can kind of see your original graph is the green one. The y-axis reflection is that f of negative x. Notice it's got flipped over this y-axis. It just got flipped. Whereas if you do the reflection over the x-axis, notice that one just got put upside down and everything got flipped. Okay, so those are pretty easy to see once you kind of notice it. All right, so back to where we were, and this is basically all those things just written out for you. These are the things you're going to be tested on, and that's why sometimes I'll put these notes in here so you know this is what you need to know. Sometimes there's extra stuff in those supplementary notes. So what we're going to do is we're going to apply these rules to some graphs. All right, guys, at this point we're going to move into our examples. I have 3 of them. I have one that's just a line. I have one that's an absolute value, one that's a quadratic function. So we're going to go through those 3 main parent graphs. So for the first one, actually for all of them, we're going to go through the exact same questions. We're going to graph the function using our transformation rules. And then we're going to find that parent graph, the actual transformations, like did it go up, left, down, right, did you flip it, whatever. Then we're going to find the x and y intercepts, which are going to take a little bit of algebra. And then we're going to find the domain and range. So the process for this, I'm always going to find these 4 things first. I'm going to find those 4, and then I'm going to graph it. Once I have the graph, then I can do the domain and range. But again, I want to be able to see the graph before I do the domain and range. If you don't recall what that domain and range is, I'll go over that when we do our graphs. So for this first one, our first graph is going to be based off of a line. And again, as you see, there's no x squared in here, no x squared out here. There's no absolute values. It's just the x with a bunch of numbers and transformations being applied to it. So this parent graph is just going to be y equals x. You can also go f of x equals x. It doesn't really matter. So that's going to be that first part. Second are the transformations. We want to look at each number. So if you think about putting all these transformations together, and let me actually kind of shove those up here. So all our transformations kind of put together is going to look something like this. So it's going to be y equals a times f of x plus or minus h plus or minus k. Now there, as we talked about, there's that horizontal compression and horizontal stretch. Well, those do apply, but we don't really deal with them that much. Otherwise, I'd have a b x plus or minus h in here. It would be something like that. But we're not really dealing with it. So it is there. I'm not really going to be messing with those. So these are the ones we're going to be looking at. So a is the number in front, x is the number being added, or h is the number being added or subtracted from x, and k is the number being added or subtracted to the function as a whole. So for this first one, we have the 2. So our first thing is going to be that 2. That is going to be a vertical stretch of 2. By the way, as I'm going through this, we're always going to go from left to right, and that's how we're going to do our graphs as well. So the first thing I would be applying is any vertical stretch, or just being aware of it, and then I will do my horizontal shift and then my vertical shift. But we are going to go in order, which means I'm going to go right 3, and then I'm going to go up 1. So those are going to be your 3 transformations that we're going to be applying to this graph. And again, we're going to apply those in order. So next up, I'm going to find my x-intercept. So in order to do this, you got to remember an x-intercept is always going to be x, comma 0. The key is that 0. So when you're finding an x-intercept, we're going to call y, or f of x, 0, and we're going to solve for x every single time. The only thing that'll change is going to be your function. So I have my function, I set it equal to 0, so now I'm going to go ahead and solve this. So this is now going to be subtract 1 from both sides. And again, it is a tight space. You'll see me kind of trying to work vertically, but I can't. So I'm going to come back up here. So this will be negative 1 equals 2x minus 6. We're going to distribute that 2. Next, I'll go ahead and add 6 to both sides. So that's going to be 5 equals 2x. And finally, I will divide both sides by 2. So I end up with x equals, you can either call it 5 halves, or you can call it 2.5, whatever you want to call it. I'm going to call it 2.5. I am a big fan of fractions. Normally we're going to use fractions, but if we're graphing it, we're going to need that decimal. So I'm going to label that as 2.5, comma 0 for my x-intercept. Alright, so that's your x-intercept. Next up is going to be your y-intercept, and this one works similarly to x-intercepts, except that we are plugging in 0 for x instead of y. These are actually easier to solve because your functions are set equal to y anyway, so you don't have to actually solve, you're really just evaluating. And you're evaluating at 0, which is an easy number to plug in. So your equation is going to look like this: y equals 2 times 0 minus 3 plus 1. So I plug in my 0 for x and do my solving. So 2 times negative 3, that's going to be negative 6 plus 1. So we end up with y equals negative 5. So the point is 0, negative 5. So I have some points now that I can work with. Now, because this is a line, this is a little simpler. You only need 2 points to graph a line. So if you think about it, the x and y intercept, those are your 2 points. So all I need to do is just make sure my stretch, which is my slope, if you haven't realized that, I don't know if I mentioned it or not, so I guess I will now. This represents your slope for a line. Now, we don't have slopes with quadratic functions and things like that, but we do have slopes for lines, and you'll see how we can apply that slope concept to absolute value equations as well. So at this point, I'm just going to go ahead and graph this. I'm ready to go. So I'm going to label my points first: 2.50 and 0, negative 5. And I'm just going to connect those points with my line. And again, all I do is just double check that the slope does work. So like if I was counting up and down and all that, I can just go and look at this. I'm going up 5 and right 2.5. Well, if you divide, rise, and run, 5 over 2.5 is 2. So this is correct. Everything's good to go. And now the only thing I have left to do is my domain and my range. So the domain and the range in this case, the domain, this is going to be the set of all x values, where the range is going to be the set of all y values. So in other words, what x values could you plug into this function? What y values could you plug into this function? Now, here's a big hint for domain. All the domain answers for right now, because we haven't gotten any functions that have restrictions, all these are going to be the set of all values from negative infinity to positive infinity, which in other words is all real numbers. So the way this works again is that set notation, which means start with the smallest value first, comma, biggest value second. So at that point it's just going to be negative infinity, infinity. Technically you would use brackets. Technically you would use brackets if you were going to want to include these numbers, but you don't technically touch infinity, so we use parentheses. Also, if you wanted to, you can use this symbol, which is a little double vertical line R. That represents all real numbers, so you can use both of those. And that's the one I prefer to use, and you'll see me use a lot. So the range is going to be the same thing because this graph goes up and down forever, so I'm going to use that all real number symbol on that one as well. Okay, so that's going to be your domain and range because basically a line goes left and right, up and down forever. So it's kind of simple. All right, next up, moving on, we have our absolute value. So this one, we're going to go from left to right as well, but let me start with my parent graph. Okay, so parent graph, we're just going to write down what our original parent graph was, try to get the colors the same. So this is going to be absolute value of x. So that's your parent graph. Okay, next up we do the transformations. We just write down all the different transformations that are occurring. So I'm going to do that here. So this one, we have a negative. We have to look at that negative. I'll even kind of put the symbol here. The negative is a flip. I like to say flip as a reflection over the x-axis. So that's your first one. Your 1/2, that's going to represent your vertical compression. And I'm going to add a little note in here. It's basically the slope. Remember I said the absolute value basically comes from the equation y equals x. So these are kind of lines. It's a V shape, but it's kind of like a line. So that 1/2 will represent that slope of those lines that are kind of coming off from the vertex. The +1, that means you're going to go left 1, and your +3 means you're going to go up 3. So those are all your transformations, a lot going on there. Again, getting my colors right. We got dark blue here. Okay, got it. So my x-intercepts, this is the one that takes a little bit of work. We're going to remember this is x, 0. So I'm plugging in 0 for y. I'm going to do some math. So this is good that we were doing some of this earlier with solving equations, so we can just apply it here. So that's my original equation, and I'm just going to go ahead and solve that for x. So start off, I'm going to subtract 3 from both sides. So if I do that, I have -3 equals -1/2 absolute value x plus 1. Now again, if you understand what I'm trying to do here, I'm trying to isolate that absolute value. If I'm able to do that, and then we're going to set up our two equations. Remember, absolute value, you just set it equal to the number and then the opposite of that number. So that's what I'm trying to do right now. Let's get that absolute value by itself so I can set up my two equations. So next step, I'm just going to go ahead and multiply both sides by the reciprocal. So when you do that, you end up with +6 equals absolute value of x plus 1. Okay, so now that you have that, we can set up our two equations. The first one is going to be x plus 1 equals 6, and the second one will be x plus 1 equals -6. So I'm going to get 5 and -7. So remember, 5, 0. -7, 0. Those are going to be your two x-intercepts, and you should have 2 or 0. I guess if it's like above the x-axis, it opens up, you'd have 0. You can have 1 only if it's the vertex that's touching the x-intercept or the x-axis. Otherwise, like I said, normally you're going to get 2. So that's going to be your those are going to be your x-intercepts. And now we move on to the y-intercept, which I did like an orange here, so let me do that. Alright, so remember, y-intercepts are going to be 0y, which means you're plugging in 0 for x. So this is going to be, in this case, y equals, or you can say f of 0, if you're doing like, evaluating functions. But that's -1/2, 0 plus 1 plus 3. So again, a little bit of math here. 0 plus 1 is 1, so this will be negative 1/2 plus 3. And because I'm going to keep the decimals here because we're putting it on our graph, I'm just going to 3 minus 0.5 is 2.5. So I'm going to have 0, 2.5 for my y-intercept. Okay, so with that I can go ahead and graph this. So I'm going to do that now. So we start off with our transformations. So we know the graph has a point at 0, 0. Kind of show you how this works. So I'm going to take this point, which is at 0, 0. So you can kind of see it here. It's at 0, 0. That's the vertex of that V. Okay. So I'm going to take this and I'm going, again, it's going to get flipped over the x-axis. So I know when I graph it, it will be going upside down. I need to know that. But from there, I am going to, looks like I'm going to go left 1, up 3. So left 1, up 1, 2, 3. And I got my point. Okay. So I went left 1, up 3. Now again, a couple of these other things, I have some points I want to label. I have one at 5 at 0 and negative 7, 0. So I'm going to label that. So 5, 0 and negative 7, 0. That's enough for me to graph this, but I also have a point 0, 2.5. So that's about right there. So it should all fit. If it doesn't fit, you may have screwed up. Either that or your scale on your graph is terrible. If you're using graph paper, that won't be an issue. So there we go. Okay, so it's not the best. It looked like my line kind of off center there, but you can kind of see it. Okay, so anyway, at this point, the only thing I'd really have to do is, to make sure this is right, is make sure my slope is, is going to be negative 1/2. Really, it's the 1/2 and it's flipped upside down. So you can kind of figure that out anyway just by using the points that you already have. So I have this, this negative 1, 3, and I'll use this 5, 0, and just double check the rise and the run. So I go down 3 and right 6. Negative 3 over 6, that works. So I'm good there, and it looks like I'm going left 6 as well. So I'm going down 3, left 6. So it's 1/2 either way you look at it. So my slope is good. So everything's fitting just fine. So now I can do my domain and range. So when you're doing domain and range, as I told you, the domain on all the functions we're doing so far is going to be all real numbers. So I'm going to use that symbol for all real numbers. And again, that's for all of them, okay, for now. When I say all of them, I don't mean when we do lessons later this year. But for right now, for this test, this unit, your domain's all real numbers. You better get that right. All right, your range. Now this one does not have a range of all real numbers. Notice it doesn't go, there's no points up here. It stops at 3. That's as high as it gets. So our range will have a restriction. We do start at negative infinity though. It does go down forever, and we always start with the smallest value. So work from the bottom up. So you go up, 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 up until you get to this y value. It's, again, range is with your y values. We're going to get to 3. We do touch 3, so we're going to put a bracket on that 3. It means we touch it. And there's your range. Okay, so that's going to be your absolute value. And this is about as crazy as it can get. I mean, I just about threw everything I could at you on this one. Okay, so that's going to be your domain range, your graph, and everything you need to know for absolute value. Again, every function is the same, it's just a different parent graph. So if I did this with a quadratic function, it would be the same work, just a different function. All right, speaking of quadratics, here's our last one. So this next one, we're going to do quadratics. So again, to get started, again, I'm big on color, so here we go. Oops. All right, so this first graph, or for this next graph, the parent graph is going to be y equals x squared. You kind of see it's just a parabola, it's that x squared function. The transformations, we have only 2 of them here. I have that 3 in front, and then I have the minus 4. Notice the minus 4 is not in the function because that minus 4 is not being squared. So that's going to be your k value. So your first value is that 3. That's an ugly 3. I'll fix that. So the 3 is a vertical stretch. Again, that number is bigger than 1, so that makes it a vertical stretch. And your minus 4, that means you're going to go down 4. So not much going on here, really. So that's that. And talk about my colors. I'm going to change it. Don't worry. Power technology. Okay. Done. Alright, so next up I'm going to do my x-intercepts. X-intercepts in my dark blue. So here we go. That's too dark. There we go. Alright, remember the x-intercepts are going to be x0, so we're going to work with that. So in this case, my x-intercept, I'm going to plug in 0 for y and solve. So we're going to go 0 equals 3x squared minus 4. So here we go. Plug this in and see what we get. I'm going to add 4 to both sides. This one doesn't take as long, although the answer will be kind of ugly. But we'll be fine. So this is going to be 3x squared equals 4. I just put the x squared on the left because I want to. I'll divide by 3. So x squared equals 4 thirds. And this is where we probably can use a calculator if I can get this to work here. So I thought I had my calculator up on my iPad. I don't. So I'm going to go ahead and square root this. I got a calculator here. 4 thirds. Just plug it in your calculator and see what you get. And this is going to give me about 1.15. And again, you have to realize when you do this, if you didn't think about it already, you got to put a plus or minus in front of it. It's 1.15 plus or minus. When you square root, it's always plus or minus. And you think about it, this is a quadratic. It's going to be U-shaped. It's going to be opening up. It's going to touch twice. We have to include both answers. So we're going to have negative 1.150, and we're going to have positive 1.150. So those are going to be your x-intercepts. And we'll put those on there in just a minute. Alright, your y-intercepts. It's orange, yep. So that's going to be 0, comma y. We're going to plug in 0 for x and evaluate. So got your function up here. It's going to be y equals 3 times 0 squared minus 4. And if you kind of look at this, it kind of works the same way as a slope-intercept form. The constant is your y-intercept. The reason for that, anything being multiplied by 0, which would be any term that has an x in it, would be 0. So the only thing that's not getting touched is the constant. So this is just going to be y equals negative 4. So 0, negative 4, is going to be your y-intercept. So I have my points. I should be good to go here. So I'm going to go ahead and graph this, and then I'll do my domain and range. So I'm going to label my point at 0, negative 4, and I have my points at 1.15 and negative 1.150. So just over 1. So we need to make this graph kind of look like a parabola as best we can. So again, it touches that point, that's your vertex. Come up here, and we are good. That's going to be your quadratic function using your translation rules. Okay, so here, remember I said domain and range. Domain's always all real numbers, don't forget that. But the range, well, this one has nothing below negative 4. So our range is not going to be all real numbers. It's going to be restricted. So if you start at this, you always start at the bottom. The smallest value is going to be right here at y equals negative 4. Again, this is 0, negative 4. So that's where your range will begin. So you're going to go negative 4, bracket, up to infinity. It will go up forever. So that's going to be your range. Alright, so that is transformations of functions. Hopefully you learned something, and you can go ahead and apply that now. Good luck.